So today I'm going to present a working paper called Deep Learning, Jumps, and Volatility Burst. So basically it's a paper about how technology and machine learning can help us solve old financial questions, which is basically how to detect jumps. So in this presentation, it's going to involve a little bit of neural networks and stochastic differential equations. So if someone is not comfortable with that, you can just ask me, interrupt me, I will gladly answer that. So basically, it's popular in finance to model stock price evolution using a jump diffusion model. So basically, you said that the change in the stock price is going to be given by a first term, which is a drift, then some continuous noise called the Brownian motion, plus some discrete noise called a jump, or so basically discrete jump. So now the Brownian noise has some particularity, which is in theory, it has continuous path. The jump noise has discrete path. So now if I ask you, given some stock price evolution, how many jumps did you have? In theory, it's trivial to answer that question because you just observe where it was continuous, this is the Brownian, and as soon as you have some discontinuity, this was a jump. Now in reality, problem is that we don't observe data in continuous time. In reality, data is discrete. So now, given the same price, the same path, if I ask you now, where did you have a jump? This is not an easy question. And this is exactly what we try to answer. So, so we try to identify jumps, disentangle them from volatility bursts at some reasonable frequency. So we are not the first one to try to do this. Many statisticians have tried before. All we try to do is propose some technological advancements, some AI technique that will help us do that task better. And I believe that the idea is more general than what I'm really doing. I think this idea can be generalized to many problems in finance. So basically, what do we propose? We propose a non-parametric, model-free way to detect jumps. We don't use any theoretical assumption on the data generating process. And we significantly outperform the statistical methods in terms of type 1 and type 2 errors, which is false positive and false negative. And how do we do that? We use long, short-term memory networks, which are really great at handling time series data. So basically, I'm going to very quickly present what already exists, and then try to convince you that we can do better. So what already exists is a statistical test to identify these discontinuities, these large changes. Basically, the test is going to assume the same dynamics for the stock price. And then they need to estimate this guy, this sigma. So statisticians have developed some method to do this, which uses bipower variation. So this statistical estimator, I'm not going to explain it. You just have to believe me that it exists. And I call it sigma hat. And it estimates sigma. Now, this test is going to work well if the sigma doesn't change dramatically. So if volatility of the asset prices doesn't change dramatically over time. So this is just the formula that they assume this. You don't need to understand that to get my point. So basically, they say if this guy doesn't change too quickly, doesn't jump, basically, we have a good test. The problem is that in reality, it jumps. So the current statistical methods are not able at handling this kind of environment. So basically, so there is a paper by Token and Todorov that shows that volatility does jumps. So basically, the assumption of the statistical methods are violated. So what do? We just propose some neural network technique to solve this problem. So basically, I'm going to define what is a neural network very quickly for those of you who maybe don't know. So basically, a neural network is kind of simple. It just transforms data in some nonlinear way. So a network is simply a collection of layers, which is the vertical column. And each layer has neurons. And what does a neuron do? It does basically three things. It takes your input, which is just a vector. You can think of your input as, I don't know, picture of a cat. You want to know if on the picture it's a cat or a dog. You give this picture of a cat, transform that into a matrix. You give this picture of a cat, and each neuron is going to do three things. Multiply this picture by some matrix or vector, W, add some bias, some number, and put all of that into a nonlinear function, which can be pretty much anything you want, just has to be differentiable. all of the neurons do this repeatedly, and that's it. That's all the network is doing. Then, of course, you need to find those numbers. What is this W? What is this B? So basically, you train the network, right? The network is going to perform this operation. It's going to tell you this is a dog. You say, no, it's not a dog. You're wrong. And then you're going to change the parameters until you get it right. You do that a lot of time, and you have a neural network. So we do this, basically, but with a slightly different network. So we use what's called a long short-term memory network. It does the same thing, except that it has a long-term memory, which helps you remember what happened far in the past, and a short-term memory that's going to forget what is not important in the recent data. So basically, you just feed some data, you apply this technique, you collect the information, you compute some probability, and then you compute an error function. And then just you minimize this error function by changing the parameters that you have here. This is not rocket science. So basically, yeah, the key to the network that we use is that, I mean, in finance, in economics, usually we have a lot of time series data, and the network we propose is handling time series data very well, thanks to this long and short-term memory. So basically, how do you do that? You want a network that's going to tell you when there is a jump and when there is no jump. So you need to train it for that. I cannot train it on real data, because on real data, I have no idea when I have a jump or not. So I'm going to train it on simulated data. I'm going to simulate a lot of data using some process, which is given like this. So basically, the stock price jumps, and the volatility itself jumps as well. I generate a lot of data. And since it's simulated, I know exactly when I had a jump and when I didn't have a jump. So I'm going to label each data. Then I'm going to train the network. I'm going to say, look, there is a jump. Learn what it looks like. And then tell me later when I face a jump again. The big advantage of what we propose, training a neural network on simulated data, is that we can have virtually an unlimited amount of data. Because it's simulated, we can have as much as we want. This overcomes a big limitation in AI in finance, because usually in AI, you need a lot of labeled data, which is not easy to get. Some people use tweets, Instagram, using these hashtags. This is labels for your data, but you only have so many data. This is limited. With what we propose, at least for this kind of problems, you have an unlimited amount of data. Of course, you need some computing power to process all this data, but this is another question. So why do we use a neural network? Basically, it's great because we don't have any what's called regularity assumption on the underlying process. We can have stochastic processes that describe financial markets really realistically. They can be really complex, and the network is able to handle that, while the math in statistics is not able to handle such complicated processes. That means that we can account for various stylized facts in equity data, for instance, leverage effect or volatility jumps. Also, we train the network under different environments using different type of processes. We say, hey, look, this is what a jump looks like in this market environment. And this is what a jump looks like in this other environment. So the network learns what is a jump under different specifications. This also means that we don't have to retrain it often. So now, this is great, this is what we do, but how do we perform, right? So first, I'm going to test how the network works. So I have a network, it's trained, and now I simulate a lot of new data that the network has never seen. And then I ask the network to classify this new data. It's again simulated because I need to be able to know when there is a jump or not. So basically, first is I say, OK, volatility is not changing very dramatically, so it's not jumping. So in fact, I am meeting the assumptions of the statistical method. So it's no surprise that the statistical method is doing great here. In fact, slightly better than the network. The percentage of detection of jump is slightly higher for the statistical method, and the percentage of spurious is slightly higher for our network, which is bad. But we have proof, empirical proof, that this is not a realistic market condition because volatility is not changing fast enough. When volatility changes fast enough, so basically I just say volatility changes really fast in a short period of time, it jumps. Now the network is doing much better. This is no surprise because we violate the assumption of the statistical method. So we have a higher percentage of detections. We detect true jumps more often, and lower percentage of spurious. So spurious is when you say this is a jump, well, in fact, it was not. I mean, the statistical method has a 200% spurious detection rate in this environment. I mean, this is huge. So why does it work better, right? This is a question I often receive. Yeah, you have a black box. This is great, but why does it work? So, well, basically, the network is able to detect when volatility changes really fast, jumps, and adjust the test statistic of the statistical method accordingly. You know, it learns when volatility jumps and changes all the parameters of the test statistic. We do also some robustness check because you can say, okay, great, you trained the network on some environment, but what if reality is very different from what you trained on? So we also ask the network to classify data that's been generated by processes that it was never trained on. So not only the parameter change, but the equations themselves change. And we also train the network where the volatility paths are not simulated, but estimated from real data to make it more realistic. Now, how do we perform on real data? On the real data, we have no clue what is a jump and what is not, right? But we can still try to classify them. So I take returns of a stock called AIG from 2006. I just plot standardized returns, so return divided by volatility. This is what it looks like at a 2-minute frequency. So, and I compare both methods. Who classifies what? So first, on the blue points, we agree. We all think that this is not a jump. This is not a large discontinuity. That makes sense. On the green points, which are the large deviation, we also agree, both methods. We all think that this is a jump, right? And then we disagree on the red points and on the yellow points here. So the network and the statistical method disagree. Now, since this is real data, we have no idea who is right or not. But still, we can perform some kind of event study. We take, for instance, one event, which is this point, this little point. So the network thinks that this is a jump, and the statistical method thinks it is not. So then we look at what happened on that day, right? Was it really a jump? So on that day, it was the week when Lehman Brothers declared bankruptcy. On Friday, the State Secretary Harry Paulson made an announcement that the Treasury would save money market funds. Right? So that was a huge news, a huge event. So this happened at 10 a.m. So basically, this is the event that happened in this point where we disagree. So I just zoomed on the price of AIG on the morning. This is, again, the price of AIG at 2 minutes. So we have the conference from 10 to 10:14. And you see that right after the conference is finished, so 3 minutes later, you have this huge change in price from $278 to $314. This means that you had like almost a 12% return. And now, again, this is real data. I don't know if this was really a jump, but I think we can all agree that this looks like a jump, that the network was able to detect, and the statistical method was not able to. And this makes sense because here, just before the announcement, you had a huge volatility that seems to decrease later on. That means that you probably had a volatility jump, but a negative jump. And this is exactly when the statistical method fails, and we don't. Now you say, okay, but why do I care about jumps? I mean, I don't care about that. So jumps might be important for asset allocation, risk management, derivative pricing, or trading. And we give one example of what we do that is an application to volatility trading. Now, some of you may know that volatility is a variable that can be predicted to some extent, right? Unlike returns. If volatility is high today, it's likely that it's going to be high tomorrow. So you can trade. If you estimate volatility well, you can trade and make money with that, maybe. The question is, can we use what we just did to trade volatility better? So, yes. I'm going to define the realized variance, which is the total variance of the price. So you take the price with the Brownian noise and the jump noise, and you compute the variance. This is the total variance. Now, the idea is that jumps do not have predictive power for the future, maybe. Let's assume they don't, right? If they don't, if I'm able to remove the jumps from the price, then I can compute a variance which is called a continuous variance. Basically disentangle jumps from no jumps, that compute the variance from the part that doesn't have jumps. If jumps are indeed just noise that don't have information about the future, I just might be able to get a more precise signal about the future. And this is what we try to do. So basically, we use a simple linear regression where we try to predict total variance tomorrow or like a few days ahead at some frequency, daily, weekly, or monthly, using continuous variance. So basically, separating the jumps from the rest and computing the variance from the part that doesn't have any jumps. And we ask if this signal is able to predict volatility better. Now, how do you remove the jumps? Well, this is not an easy question, right? So you could use the statistical estimator I just mentioned before, based on bipolar variation. You could use the statistical method of Lee and Micklin that is just a benchmark statistical test, or you can use our method, neural network. Basically, you ask the network to say when you have a jump, you remove the jump, you compute the variance out of that. That gives you some variance estimates. And then try to predict the future using that. Then the question is which method performs better at predicting the future. And those are the results in terms of R-square and mean square error. And basically, you see that, so in plain vanilla is just, you don't separate the jumps from the rest. It's just like you pull everything together and you compute the variance. And then the result is that our network, using our network, we always have at every horizon, daily, weekly, monthly. So when you try to predict daily vol, at 5 days, tomorrow, weekly vol, 5 days ahead, or monthly vol, a month ahead, our network always has the highest R-square and the lowest mean square error, which gives a hint that we indeed managed to remove the jumps which were just noise and didn't have information about the future. That's it. So in conclusion, so we propose a jump detection method using long short-term memory network. We are able to disentangle jumps from volatility bursts, and we significantly outperform the current method. Now, what I just presented might be technical, or you might not care about jumps. However, I think that the idea is more general, right? You can use AI or neural network in finance trained on simulated data to solve some problem that you want, right? It doesn't have to be about jump. You can do it on something else. You just want to classify, just want to learn some property of the stochastic process. You just have to simulate it, train a network on it, and then apply it to real data. So I think what we do is just one tiny application of what can be done in general in this field. That's it.